but with factored form. So we're going to talk a little bit about the relationship between factored form and x-intercepts again. So we looked at this a bit yesterday. So we saw that factored form of a function is f of x equals a times x minus m times x minus n. And that if I want to find the x-intercept, so of course we just set the function equal to 0, right? So we have 0 equals a times x minus m times x minus n. And to solve, well, a can't be 0 because it's a constant. So we'll just set the other two factors equal to 0. And we get x equals m and x equals n, and those are our zeros. So the zeros of the function, and then that means our x-intercepts. So the zeros are just the x-coordinates of the x-intercepts, right? So our x-intercepts are m0 and n0. So we can also do this process backwards. So if we're given the x-intercepts, like we can literally do this backwards to come up with the function in factored form. So given x-intercepts m0 and n0. So again, the x-coordinates of the x-intercepts are our zeros. So that tells me that my zeros are x equals m and x equals n. And those are both equations, right? So if I want to get a 0 on one side of each of those equations, on the first one I would subtract m from both sides to get a 0 on the right. So that would give me x minus m equals 0, and subtracting n from both sides gives me x minus n equals 0. Well, if x minus m equals 0 and x minus n equals 0, then multiplying them together will give me 0 as well, right? So x minus m times x minus n equals 0. So that basically gives me a function that has the zeros m and n. The only thing that can differ is the stretch factor. So I don't know what a is. Because a is a constant, multiplying a by 0 will still be 0. So there's an infinite number of values that a could be that would still make that function have the zeros m and n. So that tells me that my function is f of x equals a times x minus m times x minus n. So notice, like, if you look over on the left and like read from bottom to top, that the process we're using to write the function is just literally doing the process of solving for your x-intercepts backwards, right? We start with our x-intercepts, we get our zeros. From that, we can get our factors by getting 0 on one side, and then that gives us our function. In practice, we'll have to solve for a as well. So in our example here, we're given our x-intercepts, and that's my clue that I want to use factored form. So half the battle with this writing quadratic function stuff is just knowing which form of a quadratic function to use. Right? Because if you're given x-intercepts and you try to use standard form, it's not going to work out too well, because standard form, the numbers in standard form correspond to the vertex, not to the x-intercepts, and then vice versa, right? So yesterday we saw that if we're given the vertex, we want to use standard form to write the function. And then today, since we're given the x-intercepts, we want to use factored form. So I'm going to start with my zeros. My x-intercepts are -6, 0, and 2, 0, which means the zeros of my function are x equals -6 and x equals 2. And again, those are both equations, right? So if I want 0 on one side of the first equation, I'll just add 6 to both sides. So we get that x plus 6 equals 0. And then subtracting 2 from both sides gives me x minus 2 equals 0. So now I have two factors that I know will multiply to give me an output of 0. So my function is a times x plus 6 times x minus 2. But we're not quite done because, again, like there's an infinite number of possibilities for a. And so to narrow it down, we're given a third point. So just like yesterday, we're just going to plug that point in and then solve for a. So my output is 21 when my input is 1. So before I start doing anything to both sides of the equation, I want to simplify the right side, right? Using order of operations, resist the urge to start distributing, because like I can add 1 and 6 and I can subtract 1 and 2. So there's no need to start distributing all over the place. Like we can just do those operations inside the parentheses to simplify. So we have 21 equals a times 7 times -1. So 21 equals -7a. And once you get to that form, then you can divide both sides by -7. So that gives us a equals -3. And so now we have all the pieces to our function. So f of x equals -3 times x plus 6 times x minus 2. And there's no need to like multiply that out or anything like that. So all three forms of a quadratic function are perfectly acceptable answers. Like it wouldn't be wrong to multiply it out, but you just open up the possibility of making like a calculation error. So you might as well just leave it in factored form. What questions do you guys have about the process? Any steps that don't make sense? Good morning. It's gloomy outside. You guys look like you're having a gloomy day. We're okay with this? Awesome. Okay, so this next example is essentially the same problem, but instead of writing the x-intercepts, like they're just giving it to you on a graph. So one thing about writing an equation from a graph is you just want to make sure that the points you choose on the graph are like really clear points. Like you wouldn't want to like try to figure out what the vertex was, right? Because like the y coordinate looks like it's about 5.2-ish, but like we don't know if it's like 5.213 or whatever. Like so we want to pick points that like are integers. And so the intercepts are always kind of the best choice because you can see exactly where they go through the axes. So we have the point 0, 4 here. We'll use that for our third point to solve for a. And then our x-intercepts, the numbers on here are tiny, but that's a -6. And that's a 2. So now that we have our x-intercepts and a third point, we can use the exact same process we used in the last problem to write our equation. So go ahead and write a function for that graph. We get f of x equals a times x plus 6 times x minus 2. Notice this function has exactly the same x-intercepts as the last one. So to get to that point, like it's literally exactly the same as this, like up to there, right? Because our zeros are exactly the same. But that doesn't mean it's the same function necessarily, right? Because a can vary. So we're going to plug in our y-intercept. So when the output is 4, that corresponds to an input of 0. Simplify inside the parentheses. And so a equals 4 over negative 12, which you want to simplify, so that gives you negative 1/3. And so f of x equals negative 1/3 times x plus 6 times x minus 2. So this kind of shows us how important it is to find a, right? Because like there's an infinite number of functions that go through those same x-intercepts. It's just a matter of like how narrow or wide they are, right? So this one and the one before it, they both go through the same x-intercepts, but that doesn't necessarily mean they're the same function, right? Whether or not it opens up or down is dependent on A, and then also like how wide or skinny it is dependent on A. So any questions on that one? As I was walking around, it looked like everybody got it. Everybody got that negative 1/3. Okay. So one other thing that we can do with this relationship between factored form and zeros is we can actually use it to factor polynomials. So we don't do it a lot with degree 2 polynomials because we have the AC method, but for a problem like this, like writing out all the pairs of factors of negative 1,728 like could be a little bit tedious, right? And so we can use the x-intercepts to factor. And where this really becomes useful is when this is how we factor higher degree polynomials. So we don't have methods like the AC method and factoring by grouping for really big polynomials that are like degree 6 and have like 5 terms. But if we can figure out their zeros, then that gives us their factors, and and then we use long division to factor. So it's pretty useful, this relationship between factored form and zeros, because it allows us to factor really big polynomials that we just don't have methods or tricks to factor. So we're going to practice on a quadratic. We typically will do it with quadratics if the numbers are big enough that like the AC method just seemed kind of like a pain. So to find the x-intercepts, I'm going to set my function equal to 0. And how else could I solve that other than factoring? Sorry? Yeah, the quadratic formula, right? So we'll do x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. So this looks kind of messy, but what do we know about the discriminant? Like, if we're asked to factor it, then that means this polynomial is factorable, right? What does that tell us about the discriminant? So it'll have 2 solutions, but what else?
It's going to be perfect.
Yeah, it'll be a perfect square, right? Which is kind of nice because that means when we take the square root, we're going to get a whole number. And so we can actually simplify this down to just like 2 integers. So what do you guys get for the discriminant? So what's under the or inside the radical?
9,216.
Be sure that you guys take out your calculators and like practice plugging this in, because it's not uncommon to make errors plugging these in, and so you definitely want to practice before the test. So make sure that you actually get 9,216 when you plug that discriminant in, and then over 2. If you got something smaller like 4,000 something or other, you probably forgot the parentheses around the 48. So there's a couple ways you can solve that. You can remember the parentheses, or you can just drop the negative. So negative 48 squared and positive 48 squared are the same, right? So if you find yourself forgetting the parentheses around the negative 48, just drop the negative completely. Because when you square it, you're going to get a positive either way. Did you guys all get it? Excellent. So what's the square root of 9,216?
96.
So we have 48 plus or minus 96 over 2. So then we're going to get 2 answers, right? We'll do 48 plus 96 and divide that by 2. And then we'll do 48 minus 96 and divide that by 2. So what'd you say? 70.
72.
Excellent.
Did we have to do this, like the quadratic formula?
Well, so if we solve it by factoring, it defeats the purpose of using the zeros to factor it. You know what I mean? So the problem is asking us to write it in factored form using the x-intercept. So if we find the x-intercepts by factoring it, then it's kind of like a circular thing, right? You're starting with the answer to get the thing that you're going to use to get the answer. So on the test, like the okay, so this gives us x minus 72 equals 0 and x plus 24 equals 0. So remember what we noticed yesterday, that in all the forms of the function, a is the same. So what should my a be? Yeah, it's just going to be 1 because I'm given the function in general form and my a is 1, which means regardless of how I rewrite it, so regardless of what form I write it in, a is still going to be 1 because we're writing an equivalent function. We're just writing it in a different form. So it's going to be x minus 72 times x plus 24. And if you like to put the 1 there, you can put the 1 there. Good? So this next one, I feel like it looks a lot more complicated than it is. So they give you sort of a general function without all the numbers. And then they just say, like, theoretically, if somebody solved it or found the x-intercepts using the quadratic formula, they got those x values and you want to write it in factored form. It turns out that this is actually not much work because it's exactly the same as this problem, but like you're starting here because they give you those zeros, they give you those x values. And so like there's really not a whole lot that you have to do on this, so it's easy to try to overcomplicate it and like use the quadratic formula, but what they're saying is like somebody already did that and they got the zeros. So our zeros are x equals negative 13 and x equals 49. So we have x plus 13 equals 0 and x minus 49 equals 0. What's my a?
8.
Yep, again, we're given this. A is always the same. So we have 8 times x plus 13 times x minus 49. That wasn't too awful, right? just one of those things where you have to like resist the urge to make it more complicated than it is. Good? Okay, so we're going to do one more thing today. We're going to talk about finding the vertex of a quadratic function when it's in general form and factored form. So yesterday we looked at, like we noticed we could find the vertex really easily when it was in standard form because like that h and k were like actually in the function. But we didn't really talk about how to find the vertex if it was in a different form. So one thing we notice about parabolas is that they're symmetric, right? So if you were to fold a parabola, like on the vertex, the two sides would match up. So that means that if I have 2 points at the same height, they have to be the same distance away from the vertex. Otherwise, if I fold it on the vertex, those 2 points aren't going to match up, right? So that means my x-intercepts are equal distance from my vertex. So my vertex is halfway between them. How do you find the number that's halfway between two other numbers? You do what?
Divide by 2.
What do you do before you divide by 2?
Add them together.
Yeah, you add them together, right? So you take the average of them. So you add the two numbers and divide by 2. So we are going to average our x-intercepts. So if we were to set this general function equal to 0, then we would get the x-coordinates of our x-intercepts using the quadratic formula, right? So that means that we have 1 point here is negative b plus the square root of b squared minus 4ac. Trying to write this really little. AC over 2a 0. And then my second x-intercept is negative b minus the square root of b squared minus 4ac over 2a 0. So I have x values for my two x-intercepts, and I want to average those. So I'm going to add them together and divide by 2. So we have x equals, so negative b plus the square root of b squared minus 4ac over 2a plus negative b minus the square root of b squared minus 4ac all over 2a. And then I have to divide that whole thing by 2. So this looks pretty messy, but what I notice in the numerator is that the two fractions I'm adding have a common denominator, right? So all I have to do is add the numerators. And the fraction on the left has a positive square root of b squared minus 4ac, and the fraction on the right has a negative square root of b squared minus 4ac. And so when I add them together, I just get 0. So these add to 0 because they're exactly the same except they're opposites. And so that makes this a lot less messy. In the numerator of those two fractions, I just have negative b plus negative b. So I'm going to get negative 2b over my common denominator of 2a, and that whole thing divided by 2. So then in the numerator, these factors of 2 will cancel because 2 divided by 2 is 1. So we have x equals negative b over a divided by 2. And dividing by 2 is the same as multiplying by what? 1/2, yes. So we have negative b over a times 1/2. And that gives us negative b over 2a. So this tells us this x coordinate right here. So that's the x coordinate of the vertex. It doesn't tell us the whole vertex because the vertex is a point, but it does give us the x value. So we call it the vertex formula. The vertex formula gives the x value of the vertex. So x equals negative b over 2a. And notice, just like with the quadratic formula, there's two sides to every formula, left and right side. We need to write both sides. Otherwise, we just have a bunch of numbers floating around and we're not quite sure what they mean. So always write your x equals. So now I found, if I find the x value of my vertex, how would I find the y value? If I have a function.
Set y equals 0, plug in.
So if I set y equal to 0, then that would correspond to these 2 points right here.
So just plug in.
Yeah, we're just going to plug in the x value. Remember that the y value of any point is just the function evaluated for its x value. And so the vertex the x value is negative b over 2a, and then the y value is just f evaluated for that, which looks a lot nastier than it is. Like when you have actual numbers, like negative b over 2a just turns into a number, and we're just plugging that into our function. So let's find the vertex of this function. This is where like the vertex formula is especially convenient. Like we're definitely not going to like factor that, right? Or put it in standard form. So we'll use the vertex formula first to find the x coordinate of our vertex. So x equals the opposite of b, so positive 9 over 2 times a. So again, get out your calculator and try plugging this in. It's easy to plug this in incorrectly. If you have a fraction button on your calculator, I would recommend using it so that everything's in the right place. So x equals negative 0.8. And then we haven't found the vertex yet, but we found the x coordinate of it. So now we want to find the y coordinate. So we'll evaluate our function for our x value. Plus 12.9. So again, you want to just plug that whole thing in your calculator, parentheses and all. Careful not to drop the negative on that first coefficient. That's the one I always end up dropping if I forget one. So we get f of negative 0.8 equals what?
16.5.
I'm taking his word for it. Did you guys get the same thing? No? So make sure you have your parentheses. And again, like this negative right here is super easy to forget. So make sure that's there. And definitely don't do it in pieces. Like just type the whole entire thing, like exactly how you wrote it. Because then like your calculator can do order of operations for you and you don't have to worry about making a mistake. Audrey, did you get it?
Yeah, it wasn't negative.
Cool. So then my vertex is negative 0.8, 16.5. So now we have a nice way of finding the vertex for if our function's in general form and if it's in standard form. And this also really gives us a way to find it if it's in factored form also. So if your function's in factored form, definitely don't like distribute just to put it in general form so you can use the vertex formula. Remember how we got the vertex formula was just to average the x-coordinates of our x-intercepts. So we just average our zeros. So if I have a function in factored form, for instance, I know my zeros are negative 13 and 49. So the x-coordinate of my vertex I can find just by averaging those zeros. So x equals negative 13 plus 49 over 2, which I think is like 18. And then again, like to find the y-coordinate, you would just plug it into the function. But see how we don't have to like go through the trouble of distributing just to use the vertex formula? Because if we remember how we got the vertex formula, we can just apply that to these zeros. So we're just averaging our zeros to find the x-coordinate of the x-intercept. So, or of the vertex. So now we have a way of finding the vertex regardless of what form our function is in. The vertex is really helpful because remember those application problems we did the other day where we found like the maximum, or we found like the dimensions of a rectangle that would maximize area and things like that. So now we have a way of finding the vertex of those functions like without the graph, so we can find it algebraically. So that's what we're going to do for the next 2 days, is work on maximizing and minimizing algebraically rather than graphically. So there's some problems on the back there. We don't have a ton of time.